In this lesson, we're going to look at interpreting the derivative and also estimating the derivative. And when we're estimating, it's going to be very similar to what we did before with using msecant, but in this case, we're given a table of values. So first, we're going to interpret the derivative. If you look at just the very first example here, we're given that f of 5 is equal to -3. So this is a point on the graph of f of x. The other piece of information we're given is the slope at x equals 5. So f prime of 5 is equal to 2. That means the slope at x equals 5 is 2. And we learned from the last lessons that we could write this as dy over dx, where y is f of x. So dy dx is equal to 5. So x is equal to 5 here. This is 2. So our derivative of y at x equals 5 is 2. Now, I drew a picture to represent what that could look like, and you could draw that as well if you wish. So let's just say this is our graph of f of x. We pass through the point 5, -3 in this original graph, and the slope should be 2 at that specific point. That's our m tangent. So there's a couple of ways we could say this. We could say the slope of m tangent is 2 at x equals 5. We could also say the slope of the curve is 2 at x equals 5. And we could also say the rate of change of y with respect to x is 2 as well. So I'm just going to summarize all of this down. So the slope of the tangent to f of x at x equals 5 is 2. You could also say the slope of the curve f of x at x equals 5 is 2. And lastly, you can say the rate of change of y. It says here that y is equal to f of x. So the rate of change of y with respect to x is 2. And lastly, one that I just wrote in here, you could also say the y is increasing twice as fast as x at x equals 5. So in other words, your slope is increasing twice as fast at x equals 5. We're going to look at example 1. This is where we're going to interpret the derivative, where a is our area and r is our radius. So we're looking at the rate of change. Remember, the derivative, the prime, is the rate of change in a. And we are talking about with respect to the radius, the r. So your rate of change of the area with respect to the radius. I'll give you a numerical example. Let's just say that dA dr, where r is 3, is 21. So let's say that we want to interpret this. So remember, d over dr, this is the rate of change of the area. And the rate of change is 21, while your r is 3. In other words, the area is increasing 21 times faster than the radius. So when the radius is 3, the area is increasing 21 times faster than the radius. Remember, this gives us the rate of change. Now try the one below, and when you're ready, reveal the answer. Okay, so in this case, we're given v, which is velocity, and our t is time. So we're looking at the rate of change in your velocity with respect to t, and that is in seconds. So your rate of change of velocity with respect to time. That's what v prime of t means. Now, if you're looking at the actual numerical example, we're given v is 3 meters per second, and t is 7 seconds. So if I want to rewrite this in terms of v prime of t, this is what it looks like. V prime of 7 seconds is equal to 3 meters per second, or dv dt at t equals 7 is 3. So what does this mean? This means at time t equals 7 seconds, your velocity is increasing, or it could also be decreasing in this case because we're not given the direction in your velocity. So the velocity could be increasing or decreasing at a rate of 3 meters per second. Okay, so this is velocity is 3 meters per second. When you're looking at the rate of your velocity, it would be 3 meters per second. Or in other words, this is also your acceleration, which is meters per second squared. In summary, when you're looking at the derivative of velocity, you're actually going to get an acceleration value. Okay? So in summary, the acceleration at t equals 7 seconds is going to be 3 meters per second squared. That's the same thing you're going to get by just reading off of this. Okay, example 2. We're going to estimate the derivative using this table. And we're going to use our symmetric difference formula for that. So it's going to be from the very first lesson that we had. In other words, we're going to use msecant and try to approximate t equals 9. So around t equals 9, we have t equals 6 and t equals 12. To find the symmetric difference, we're going to use this because 9 sits in between that. If we use 9, well, 9 is just a point, and I want to find the slope at that point. So the best way for us to do that is probably just find the symmetric difference around 9, which would be using 12 and 6. So using msecant is about your y values, which is 16, and the other y value, which is 12.57, divided by 12 minus 6. This is going to be about 0.572. So if we look at the context again of what we're actually solving for, the time t is measured in hours with t equals 0 at midnight. And the other ones are wind speeds, so w prime of t is the wind's velocity with respect to time. So this is what we found, is the rate of change in the wind's velocity with respect to time. So I'm just going to summarize that here. This is the rate of change of the wind's velocity with respect to time. So try the next question, and then when you're ready, just press play to reveal the answer. So again, for this, we're going to use a symmetric difference. In this case, we have Kathleen skates on a straight track. She starts from rest from a starting line at t equals 0 for an interval of 0 to 12 seconds. Kathleen's velocity, which is k, is differentiable and increasing. Values of k of t at various times are given in the table below. So if we're looking at the derivative of k of t, which is k prime of t, we're looking at the rate of change to Kathleen's velocity with respect to time. So we're going to find Kathleen's acceleration, which is k prime of t, because that's the rate of the change of the velocity, at t equals 4 seconds. If we want 4 seconds, it's going to be right in between here. Then we're going to use 3 and 5 to do that. And then we'll use our symmetric difference formula, and what we're going to find is 5 over 2. And because we're looking at acceleration, this would be feet per second squared, because the original velocity is feet per second. And this last example is just to show you how to find the derivative of a specific derivative using your TI-83 or 4. Now, if you don't have a TI-83 or 4, I really, again, suggest you do so you can use this on your final exam, because those are the only really type of calculators, or another type of graphing calculator that you can use. Cell phones won't be allowed on the exam at all. If you don't have it for now, I'm just going to use an online system to find the derivative. And in this case, it's called Wolfram Alpha. So you can do wolframalpha.com, and then you just type in exactly what you need Wolfram Alpha to do for you. So we can write derivative of, and then our function. And in our first example, it's 2x sine x. So I just wrote the derivative of 2x sine x, and then I gave Wolfram Alpha the value so it can evaluate it. So the derivative of 2x sine x, where x equals 0, the result is 0. So I can just write that in here. So f prime of 0 is going to be 0. Now we can do the next one into our Wolfram Alpha, or again, if you want to use your TI-84 or 3, you can do that as well. And I also have the listing here of what to do with your TI-83 or 84. So if you have one of those, you're going to press math and then 8, or you can scroll down until you see this n-deriv. Enter. Then your variable should be x. So it looks like d over, and you're going to put x right in here in your calculator. And then you're going to insert what that x value is going to be. In this case is 3 over 2, or 1.5. And then you're going to insert your function. Make sure you put the appropriate brackets in. So it's going to look like this in your calculator. I'm going to do another bracket here for the numerator, 3x squared plus 2x minus 1, then divide by ln x, close bracket. Okay, so this is exactly how you should type in your calculator. And then when you're done, you just press the equal sign. And you would get negative 8.353. And that's it. Okay, so make sure you check the homework section in your OneNote to see the homework related to this lesson.